and welcome.
Thank
Welcome
you. Yeah,
to the
thank
new
you.
lab.
Thank you. I'm happy to be here. I'm sorry I'm not here the whole time. Life goes on. Things happen. So as Colin said, I'm at the University of Miami. I'm a physics professor. I'm an associate dean, but I'm a physics professor. So I come at things from that point of view versus some of the other points of view you might have heard. So anyway, so today I'm going to talk about inelastic scattering in the ocean. And remember freshman physics? How many people enjoyed freshman physics? Okay, good, a couple. That's about the ratio that I expect. Okay, do you remember we had, during freshman physics, they spent a while talking about collisions? Remember doing all those things, trying to do collisions? How many people took, the code word is university physics versus college physics? How many people took physics with calculus? How many took it with just algebra? Yeah, okay. So the people with algebra tended to have the ones that you have a bunch of equations and you just work through these equations versus the ones with calculus. We try to explain more about what's going on. You spend way more time on collisions than you think you need to, probably, but there are two types of collisions. The reason we do that is because it's so important to understand how energy is transferred in the system. Do you remember what the difference was between elastic collisions and inelastic collisions? Anybody? So you're all graduate students, right? So it probably wasn't more than like 6 years ago that you took this class. Yeah. Okay. If you have so you have a pool ball collide on a pool table. Is that an example typically of an elastic collision or an inelastic collision? Elastic. Okay. And when you were trying to figure out how everything moved around, what could you use in an elastic collision? What properties were conserved? Conservation is everything. So what properties were conserved in an elastic collision? Energy was conserved. Anything else? Momentum. Momentum is always conserved. So that's good. So mainly, and energy as a whole is always conserved too, right? But the thing that comes out with elastic collision is when things come in, you have a certain amount of kinetic energy and you have momentum. When it leaves, you still got this kinetic energy. There's no energy that's been transformed into something else. Okay, so in elastic collision, you conserve the kinetic energy and you conserve the momentum. And can you give me an example of an inelastic collision does not conserve kinetic energy, but does conserve momentum? Can you give me an example of an inelastic collision? If I take my car and I run into a wall, okay, am I going to conserve energy? Well, am I going to conserve energy? That's a good first question. Yes. Yeah, why? The energy must go somewhere. Yeah, you always conserve energy. It's just, am I going to conserve kinetic energy? No. What's going to happen to that kinetic energy? It's going to turn into heat and deformation and all sorts of other things in my car. So basically, an inelastic collision is something like that, where something comes in, energy is transformed somewhere else. So we're going to talk about inelastic scattering, and we just went over this. Energy is not lost. So elastic scattering, photons come in and down the process with the same energy. In terms of photons, we mean they come out with the same wavelength. And inelastic scatterings, they come in with one wavelength, and during the process, something happens. Energy is transformed somewhere else, and when they leave, they're come out with a different wavelength. Okay. Anybody remember what Compton scattering was? Okay. When the wavelength changes, when it comes out, right? Okay, that's good. Do you remember why Compton scattering was important? I tend to go off on the weird things. Okay, so you remember why, especially with physics stuff like this, where it's trying to remind you why you learned this stuff. So for Compton scattering, remember why people didn't mention it? Why it was important. So the reason Compton scattering was important was that was probably one of the experiments that proved that there were photons, that actually there were discrete things. What happens in Compton scattering is the photon comes in and interacts with an electron. And when it finishes the collision, you can calculate how the electron moves out and how the photon moves out by treating the electron and the photon as discrete billiard balls, different mass, whatever. But anyway, so they come off like that, okay? So that was the proof that there are really discrete photons that act like particles. Okay, the difference between this sort of thing and fluorescence is basically, you talked about fluorescence already, right?
Or, yeah, after you.
But just now? Okay, well, so we did talk, you did mention, I thought I looked at the schedule, you had something about fluorescence a little bit. No, you learned it anyway. The difference basically is lifetime between inelastic scattering and fluorescence of the lifetime. Inelastic scattering is something that occurs very, very quickly, and I'll show you why in a minute. Now I'm gonna get Kurt mad at me, but so he has to start yelling at me when I say it the wrong way. It's like the noodles, right? That's the way I'm supposed to say it. And then I can't remember how to say the noodles. Raman scattering. Okay? So anyway, so Raman scattering is a process. Well, you're just stand in for him and yell at him. So basically, excuse me here, potential spam. Okay. So strongest Raman scattering is a strong, evident in natural, strongest inelastic scattering process in water. Although, so it occurs in water, it occurs relatively weak compared to other substances. And so what this curve is excitation at 532 nanometers. So if you take a 532 nanometer laser, send it to the water, and you look at the what you would get out, basically you'll get a lot of scattering at 532, but then you'll also get this peak where you get light coming out at about 650 nanometers. So it's taken light at the blue and shifted some of that energy over into the red region. Let's see. So the black line is the spectrum of the light that would come out in the red. Raman scattering is also polarized, just like Rayleigh scattering, which we'll learn more about next week, I think. And forget about that right now, because you don't know about that too much. So we won't talk about that one. But basically, it's shifting light from the blue region of the spectrum to the red region of the spectrum. As opposed to absorption, you did talk about absorption.
Yes.
Right. So as opposed to absorption, and if I remember, if Colin gave sort of the same lecture as before, talked about how light would come in with some goes into absorption up there, and then it's you get a higher energy state in the molecule. And some of the light, when it relaxes, will come off as fluorescent. That's a spoiler alert. And then yeah, a lot of the light, a lot of the energy comes off. Whatever. What happens with Raman scattering is there's no real energy level up there. but you get this virtual energy level. And so you basically Rayleigh scattering is when the light comes in and goes out with the same energy. So no change. The Raman scattering leads to a Stokes scattering where light goes in and comes out with less energy. And so that energy is still, so the photon coming off has less energy. The energy's in lost in the system. And then anti-Stokes is where it goes in and then comes out with more energy, higher. Basically, blue light would come out, very low probability would come out though with a bluer photon, higher energy photon. This intermediate energy level up there is virtual energy level. It cannot exist for very long. It basically works because of the uncertainty principle, which is sort of cool that you can have an energy level as long as that energy level times the time that it exists is less than Planck's constant. You have something like that, it can happen, it does happen. So there basically is how Raman scattering can happen, how you can absorption that doesn't go into a normal time of energy level. The probability of this happening, these events happening, increases if this energy level, this virtual energy level, is near a real absorption level. But it doesn't want to get too close. If it gets too close, then you're going to get into a normal absorption and fluorescence process. So it's sort of a cool, two cool things. One, you just had Compton scattering, which proved there were photons, there were discrete particles. Here you get a little thing about Planck's constant and then uncertainty principle. Two great physics things in just a short slide or two. Okay. If you look at that peak that I showed you a second ago, we talked about Raman scattering in terms of energy shift, because those are what stays constant, not the wavelength shift in energy. The way you use this is that 1 over the final wavelength is equal to 1 over the wavelength. You put, yeah, he gave me one, and I don't. I'm sorry, I had it. The curve was nice enough to give me.
Okay, because it's brighter, because you want this one.
Yeah, I like pushing my hand though, you know.
I know.
Yeah. So 1 over the final wavelength is equal to 1 over the excitation wavelength minus whatever the shift is in inverse centimeters. So you put this all into centimeters, and that's how you use the equation. Basically, if you look at that peak, that curve that I showed you a second ago, it's sort of made up of 2 Gaussian peaks that shift relative to each other depending on the temperature. So as the temperature changes, you look, this is showing you water temperature versus this marker R, which is the height of one divided by the height of the other. So the height of this one divided by the height of that one. Well, it's a height divided by the width, Gaussian width. But basically, since the widths look about the same, it's the height of this one over that one. It's bigger than 1. So anyway, you look at it as the temperature increases, the curves, this marker increases, which means this one gets higher relative to that one. So by measuring the relative peak, you could actually tell the temperature of the water, right? And in fact, that was used in the 70s by these guys including Franco, with lasers to try to remotely sense water temperature. So that's one that you can use it for. Basically, that's it. So it's made up of 2 peaks that are dependent on temperature. Importance in the natural light field. Back in the early 80s, we just started getting multispectral instruments. Before then, people would have 1 wavelength radiometers. Oftentimes, they would be called photopic, meaning that they're basically centered around like eye response, around 550 or so nanometers. We started getting these multispectral instruments, and the lab I was at then I just got out of school. The lab I was at then got a 32 channel. We had 16 channels of downwelling irradiance, 16 channels of upwelling radiance. Is that right? Something like that. Okay, and 16 channels of upwelling irradiance. And it was called a MER-1032 made by Biospherics. And one of the first things when I got to the lab is my mentor, my boss, whatever, Ross Austin said, look, we got this problem. We've got this new instrument. And it's giving us really weird results. Basically, we were getting diffuse attenuation coefficients less than water absorption. Now, it's hard to do a lecture with only talking about what you've had in class up till now. I screwed up fluorescence for Colin. I'm screwing up diffuse attenuation for either Kurt or me. I can't remember who says it first. So, but basically, diffuse attenuation coefficient you can think of as for the irradiance, as you go down the water, the irradiance levels drop. You don't even know what irradiance is until next week either. So, light. Yeah. Okay, so let's make an easy definition light. As you go down in the water, the light is attenuated. Basically, approximation is absorption plus backscattering. Okay. So there's no way absorption plus backscattering is going to be less than pure water absorption. All right. And yet, when we were getting measurements, here's an example of a radiance attenuation in this case, but here's pure water absorption. And if you look, this is the attenuation between 1 and 5 meters, 5 and 9 meters, and 1 and 9 meters. And you see that down here, it's cool. All these attenuations are bigger than pure water. But somewhere around here, you start having a problem in the red, okay? Where you can't explain what's going on. You're generating light, it looks like, instead of being absorbed, it's actually getting more light. So we were seeing this with the instruments. We tried all sorts of things to figure out what was going wrong. Maybe there were leaks in the filters out of band light. It's really hard to do this in light field because you have to really block the blue light from interfering with your red light measurement. But basically, we were seeing these problems and we were trying to figure out what was going on. I spent weeks out in the parking lot. We had a big water tank in the parking lot. And so I was playing with the instruments in the water tank, trying different things to figure out what was wrong. We knew about Raman, we weren't stupid, exactly. But it was only really thought to be important for laser excitation. How should this be in natural light field? And then a series of people figured out that we were wrong. Okay. In 84, which I was playing with this thing in 85, if I could have read this paper, I would have known what the issue was. These guys wrote a paper explaining about Raman light in the natural light field. Stalin and Raman had a paper in 88. They were running around saying that it was important. Then Marshall and Ray Smith, in 1990 came out with another paper measuring in the light field. So all of a sudden, people realized this was an important problem or an important thing in the light field, and we had to worry about it. So the characteristics of Raman scattering, it's relatively weak. If you look at Rayleigh scattering, at 532 nanometers, it's about 2 times 10 to the minus 3 per meter. Raman scattering is about an order of magnitude less. Another characteristic is like water. It has a polarization properties, but it depolarizes more than Rayleigh scattering does. There's a wavelength shift, which I just told you, and the strength varies. With Rayleigh scattering, it's supposed to fall off. It's lambda to the minus 4. With Raman scattering, it's lambda to the minus 5, but it sort of depends on whether you're talking about how the excitation or the emission wavelength, because of these wavelength shifts, there's this exponent up here changes. And also whether you're talking about photons or you're talking about energy. So you need to make sure you have the right exponent for whichever way you're calculating. As I said, the energy shift is constant, 3,400 inverse centimeters, which causes a very shifted wavelength. This is just to show you what that is. If you start out here at 400 nanometer excitation, then the wavelength shift will be somewhere around 60, 70 nanometers. If you excite at 600 nanometers, then the wavelength shift will be more like 180 nanometers. Okay, so that sort of gives you through most of the visible, then we're talking about 100 nanometer shift, roughly. So why do we see it in the light field? It's smaller than Rayleigh scattering. Shouldn't be, we wouldn't think it was that important, or we didn't think it was that important. Basically, if you look at the natural light field, the red curve is the upwelling radiance in the inverse, or microwatts per centimeter squared per nanometer per steradian. So this is the light coming out of the ocean. This is the light coming in. There's all sorts of cool things going on here. You have Fraunhofer lines and also oxygen. Fraunhofer lines are like over here. You've got oxygen absorption, water vapor lines going on over here. Pretty complicated. But the main thing to notice is there's a lot more light coming down that's over here. There's very little light coming out here in the ocean, in clear water especially. Water absorption just absorbs all that stuff. So it comes that light from the ocean's fluid. Comes out like that. So when Raman's important is when the amount of light at the emission wavelength is reduced relative to the light that's available in the excitation wavelength. So if you go back to here, you're looking up over in this region, Raman scattering wouldn't be important because it's taking light from over here and shifting it over there. Well, there's not a lot of light coming into the ocean over here in the blue UV. And so it would not show up very much in the natural upwelling light. But if you look over here in this region, shift light 100 nanometers from here over into here, all of a sudden it's going to be important. Okay, and so you're going to see it there. So where Raman's important is where there's a lot of excitation light and not very much light at the emission at that wavelength. And so here is a curve of just the downwelling irradiance as a function of depth. So at the surface, basically you have pretty close to the same spectrum there, but as you go down in the water, you're getting attenuation. So it's important if there's a lot of light here and it gets shifted in here, Raman will become a dominant part of the light field, so, which is what I say here. So basically, you need to be really careful when you're interpreting results at these red wavelengths. And what this is a curve from 400 nanometers, I made a figure so you can see 400 to 750. It's the fraction of Raman light in the upwelling irradiance. And you can see that it's not as big a fraction at 400 nanometers, it's 0.1. I don't have these things big enough, sorry. For example, for your graphs, okay, but I copied it from this article and Howard Gordon didn't make the legend real big. So anyway, so basically it's not important here, it becomes a larger fraction over here. This is the upwelling irradiance, this is the upwelling radiance, nadir, same deal, it's up to like 25% of the light field coming up. And this is for pure water, but it's 25% of light field coming up is actually Raman scattering versus natural elastically generated light. What did I want to say? Oh,
You got to be really careful to interpret these measurements at down here, because these were done in 1999 and we didn't have as good a knowledge of what's going on in the UV as we do now. So whenever you look at old papers, you have, especially modeling papers, you have to realize, think about what they had to work with in terms of inputs to their model. So most important for clear water, let's see. So here's a graph showing you the same sort of idea, Raman fraction of the water leaving radiance at nadir in percent as a function of chlorophyll for different wavelengths. And once again, I say this without our knowledge of UV. So if you look for 443 nanometers, it actually increases here as the chlorophyll increases. Why do you think would that occur? Why at 443 is the emission wavelength? So where was the excitation coming from? From farther out in the blue, okay? But then as chlorophyll increases, what's going on at 443 nanometers? Stronger absorption, okay? So why would the fraction increase there? You have less at the emission wavelength, you have less light because that's strongly absorbed. And we didn't think that anything was going on in the UV. And so your excitation is still there, but your emission's at a good wavelength. There's less natural, it's all natural. There's less elastically scattered light. So that's sort of a weird wavelength. 490 now decreases as chlorophyll goes up. Why would that be? Once again, think about excitation versus emission. As chlorophyll goes up, there's less excitation now. You've moved into the region where we think at the time we thought there was more absorption of the excitation. So basically, this is sort of a weird way, but the rest of them, the fraction goes down somewhat because the excitation is going away. At 10% of the water leaving radiance. This is for, yeah, it's pretty high. Yeah. Well, this is different as a function of chlorophyll. So
Yeah, but in clear water.
yeah.
20%.
Yeah. So how do you measure it? So in the lab, there's a few ways. In the lab, you take 90-degree scattering experiments. You have to be really careful to exclude the extinction because it is a factor of 10 lower than radius scattering, but even radius scattering is hard to measure in the lab because it's hard to make the water clear enough or take the particles out enough. You have to be careful of polarization effects in the instrumentation. We can talk about that maybe when we talk about polarization. In the field, you make measurement. One way is indirectly, you make measurements and model how much should be there given what you know about the excitation field. To directly measure it, you got a problem because the light field is still pretty bright at that wavelength. So trying to figure out how to separate it. In the early 90s, basically 3 groups simultaneously, it's sort of weird how ideas come up like that, simultaneously 3 different groups. A group at NOSC, which is Farwar in San Diego. I don't know what they're called now. Anybody, do you have anybody from Scripps? You remember what on Point Loma, what they call that Naval Center now? Is it Farwar now? Yeah. Oh, could be. Okay, so that used to be called NOSC when I was there. They went to Farwar now, went to whatever it is now. So this group at NOSC was worried about it. There's George Cadwar at Texas A&M, who's a theoretician, came up with this idea, and then I had come up with the idea that what you could do is what's called the ring effect. And what the ring effect is the idea that you had those, remember the spectrum that I showed you a second ago of the solar spectrum there? You've got all these really nice sharp lines, okay? So if you look at these sharp lines, Raman scattering is a broadband effect. And so if light scatter is inelastically scattered from over here into there in a broadband, it's going to affect the shape of these lines over here. And you'll be able to see, if it's just elastic scattering, the upwelling light field will look just like the downwelling light field. But by measuring the change in that, you can get an idea of how much of the light's elastically scattered versus inelastically scattered. And it turns out, it's one of those things. To tell you the truth, how this happened, I was sitting in a room in San Francisco at AGU and daydreaming, and all of a sudden started like, you know, I could use a Fraunhofer line to distinguish elastic versus inelastic. And it was right before when I was doing my interview trips at Miami to get my faculty position, and I was wandering around in the different faculty members, but this is the experiment I wanted to do first when I got there. And I was wandering around the faculty members telling them about this, for the ones that were interested at all. And one of the guys, Joe Hirschberg, when I started telling about it, he goes, "Oh, that's the ring effect." I go, "It's what?" He said, "Oh, that's the ring effect." Okay, and he explained that this has been used in astronomy for a long time. I never knew anybody had ever done this before. So anyway, he told me that. I looked it up. Yeah, it's the ring effect. Somebody's done it. And then I found out two other guys, George Cadwar was starting to do experiment or theory on it. And these guys at NASC were worried about it. And the reason they were worried about it was at the time they were talking about satellite laser communication, SLC program. And one thing you can do is use the Fraunhofer lines perhaps to send light down in those wavelengths, because that's slightly less background than other wavelengths. So they were worried about Raman filling in those and then negating that advantage. So A&M was theory. These were for this one application. And Howard Gordon and I were working on the theory and experiment. It took me forever to explain, to convince Howard it was worth working on, which was sort of funny. And then he got the first papers out on it. Oh, well. So anyway, so there you are. Basically, you're looking at filling existing spectral lines. Here's an example. Here's 43, 48. As you go to the downwelling light field with a very high spectral resolution, this is a Fraunhofer line. You can see as you go down, this is a log graph. So what should happen is if the attenuation is occurring evenly in the spectrum, there's no change in the shape. And if you look at this, there's no change in the shape of the spectrum. Here, if you look at 653 to 659 nanometers, where Raman scattering is important, at the surface, you get this nice big Fraunhofer line. As you go down by 20 meters, the Fraunhofer line's almost disappeared. So basically, almost all of your light has been inelastically generated. And this is the real data because it's got noise in it. So I was just going to try to remember whether that was real or not. You can use this also to look at fluorescence if you want. And in fact, people have used it from helicopters to look at terrestrial plants, to fly over fields of corn or whatever, and look at plant stress by looking at the solar-induced fluorescence. Another thing I shouldn't have talked about, but anyway, and that's sort of cool. I wondered if in Shark River, because of all the CDOM fluorescence that might be there, the color dissolved organic material, whether I could see this filling in there. Basically, I couldn't see anything there. What was sort of interesting is this thing. I've never gotten any biologists to really get involved with it or interested. Basically, if you look at brain core, this is looking above a piece of brain coral, the dry tortugas in the Florida Keys. The top is the irradiance, downwelling irradiance in the red. And you can see as the day went on, this is integration time. So this is relative units. This is actually the least amount of light. This is the most amount of light. The sun's coming up during this time. It's just I've got the integration time changing to try to offset that. So it's actually going from brightest to darkest up here. You can see there's no change in the downwelling light field. But if you look at the upwelling light field, there's a lot of filling going on here. So a lot of fluorescence from the brain coral up here. But as the sun gets brighter, the fluorescence actually goes down. And you'll learn, I won't say why. Did I say why? Right. You'll find out in a minute, okay, why. Sorry about that.
No, it's, I mean, that's a really excellent example of quenching,
Yeah.
quenching by light.
Yeah. But I can't, but I haven't, I think it's very cool. But
It's very cool.
anyway. Okay, so there's Raman scattering. Anything else in the last thing? There's Brillouin scattering. Brillouin scattering is when the light, incident light comes in and is scattered off sound waves in the water. And so you'll get a slight shift due to that. Typical values, if you come in 530 nanometers, and it's dependent on the speed of sound. The wavelength shift is on the order of 7 × 10⁻³ nanometers. Okay, so as opposed to Raman scattering, where the shift was on the order of 100 nanometers, the shift here is very, very small. But the shift does depend on the index of refraction of the water and the speed of sound. Here's sort of the equation for it. Also, the speed of sound and the index of refraction depend on salinity and temperature, but most rapidly changes with temperature. So people have talked about using this also to measure the temperature in the ocean, okay? Or measuring the temperature in the atmosphere also by looking at this. I guess have another one. Because it's the sound waves in the water that you're bouncing off. So I thought I had a slide in here. I probably took it out. There's a guy, Ed Fry's lab at Texas A&M. Ed Fry was my advisor, graduate advisor. Ed Fry's lab was using this to look at temperature and remotely sense temperature. But then his postdoc continued the work in Germany, and last I knew was building an instrument to do it with a laser from a helicopter and look at temperature profiles in the ocean using this effect.
These types of inelastic scattering are really minimal in the atmosphere outside of the water.
No, this Brillouin scattering occurs in the atmosphere, and in fact, you can do it to do laser temperature profiles of the atmosphere of lidars. But note that you have to have, you're trying to separate, this is the central Rayleigh type peak, then you have these two side lobes, which is you're trying to separate something that's only, what, a fraction of a nanometer off. So you have to have very high resolution. And it can't, whatever your instrumentation is, it can't wander too much. So what you have to do is you have to lock the laser accurately, and then look at whatever it's with some filter to the side. So what they do is they lock the lasers to an atomic line, like a cesium line, so it stays right at one wavelength, and then have a detector that sort of shifts slowly back and forth. So it's pretty cool. I tried to get somebody to do that in Miami. He wasn't interested. Anyway, you could talk about this. So okay, well, fluorescence distinguished longer lifetime, longer intermediate state. When it's got excitation, it stays there longer before it emits. So there's more chance to forget information about the incoming photon. So phytoplankton fluorescence is basically isotropically emitted versus Raman scattering is like a Rayleigh scattering. You show the volume scattering function for Rayleigh scattering. So this is more isotropically emitted. I go off on these weird stories. I'll give you a lesson. What never to do. Gordon et al. 93. That was a paper Howard and Gordon and I and my wife did an experiment. My wife and I did an experiment in Bigelow during the summer. And we made all these measurements of different cultures because it's a culture center. And we brought the data back. Howard and I and Kay wrote up the paper. It's published there. When the preprints came out, so if you look at the paper in L&O, the whole paper's there. They used to put the authors at the end of the paper. One author is on the second page, the one last page, my wife's. So it's Howard, me, and my wife. Hers on a separate paper. In the old days, you just get preprints. I never noticed. Howard never noticed. They didn't print that piece of paper in the preprints, in the reprints. So basically, I show us from Kay. I'm like, hey, look, we got the reprints. Cool. Her paper, her name's completely left off of all the reprints. Don't do that. It does not do well for dinners. What's that?
At least if it's the wife you're leaving off, don't do it. You leave my name off. Don't look at that for you.
Yeah, it wasn't fun. So anyway, she actually wanted me to get them all reprinted. I was like, I don't have that much room. So anyway, it's isotropic emitted. It's probably also depolarizing, although I don't know if people have done that. But I do know they looked at used polarization, depolarization of fluorescence to separate fluorescence in the natural light field. There's these guys from City College. Anybody from City College? Didn't we have somebody this year? Yeah, okay. So these guys all did this paper, and I think there's a follow-on paper on it too. The polarization of fluorescence you can use as an indication of the lifetime of the state and how much things have changed. Okay, I'm almost done. Other fluorescent things, CDOM, fluorescence, there's excitation versus emission. These instruments, Colin's got one. By looking at signatures of different oils and such, you can separate different types of CDOM. I'm not going to go into it. You talk about CDOM, don't you?
A little bit.
Okay. Well, it's it's a very weird thing, and nobody really. The last time I looked at it, people don't understand it too well what it is. CDOM is typically measured through absorption, but you can also measure it with fluorescence. What actually is important, CDOM's absorption spectrum falls off very quickly from the blue. You can measure with fluorescence. There's these things, and now there's a whole bunch of newer instruments out there. CDOM fluorescence, for the most part, is ignored. Why do you think that would be? Yeah, so if you look here, this is the emission wavelength for excitation at 350 nanometers. And you can see it's being excited at 350. To be excited, it has to be absorbed. The CDOM absorbs really strong in the blue, right? And then falls off in the red, toward the red, very strong, quickly. It's the excitation here at 350, the emission is at 450 or so. What's at 450, what's the natural light field look like? There's a whole lot of light there, right? So basically, it's taking light from here and moving it over to where there's a whole lot of natural light, so it's not going to show up too much. It'd be really useful to have quantum fluorescence efficiency.
but those are almost rarely measured. If you have these, then you can put them into models. And Hydrolite has this in their model, right? And you're using this data by Haas and all. Pretty sure.
And Steve Haas was in the optics class,
Oh, was he?
and that was his project in the class. Is
Yeah.
He actually took the CDOM and he had to concentrate using resin. And then he measured the pond efficiency.
Yeah.
And everyone was like, oh my God, it's the first time it's ever been done. And he's like, yeah, but I'm in a rock band. And he left.
Oh, is that right? Yeah. So this is
In his master's thesis, and it is the one and only thing I have ever found that puts quantitative values on these fluorescence functions that I need to put it in the hydrolyte. And all the rest of the world just does relative values because they're only interested. It's like if you measure all your phytoplankton absorptions and you all normalize them to 1 to maximum. Well, and then all you care about is like, what is 440 relative to 550? Well, that's okay. But I need to have a real absorption spectrum and per liter to put it in the hydrolyte or Monte Carlo code. And Haas, masterpiece, never published. It's not available, but I have a copy. He's the only guy that had the numbers that I need to put CDOM fluorescence in the hydrolyte. And he did this fabulous thesis and then disappeared and has never been heard from since.
yeah, it's a Ken Carter student. Oh, you do?
So he's Ken Carter's student
At USF. Almost all, as Kurt said, almost all the measurements that are relative to cleon sulfate or some other fluorescent material, so it's hard to occur. But if you talk to any chemist, marine chemist, the things you do to concentrate it change it tremendously. So Hydrolite has this in there, but it probably doesn't have a lot to do with reality in the world. And so we need to have some way to make these measurements to do it better on unconcentrated CDOM, which is why for like years I've been trying to work with Colin and get a polarizer into her excitation emission spec. Because if you look at, oops, I'm going to, oh, well here's another example, oils fluoresce. This is an excitation at, below 300 and emission up here. But this is an example of an excitation emission spec. Here's the excitation, here's the emission. She has one of these, Colin has one of these spectrometers that does this. What you don't see here is Raman scattering shows up in these instruments. And so by having one of those and calibrating against Raman scattering, which you know the scattering cross section for, you should be able to take the CDOM and put it to a real number. The problem is that those instruments aren't calibrated real well, and spectrometers, when you have a grading or something, have polarization effects. So you can't just use it by itself. You can't just use Raman by itself because you don't really know how the polarization is working. So you need to put a polarizer in the excitation and a polarizer in the emission, which we've been trying to get around to do for 8 years, 6 years, something like that. When I'm up here in the summer, I've never managed to do it. We forget to go around, and now I have to. So I'm going to order that this summer. Well, I'm going to order it as soon today. I'll order it today. They're a couple $1,000s of polarizers. So I'll order it today. I'll probably have it shipped up so it's before the end of the time, if Edmunds has it and stuff. Anyway, why? Other things, minerals fluoresce. Mineralogists can use it, but it's not really important to us too much. So the reason that slide is in there is because the first time Emmanuel said, "Hey, give a talk on inelastic scattering." Okay, remember to include minerals. So I searched everywhere trying to know, why do I need to include minerals? And I found these sorts of things, but not for ocean optics. So
but you have it in there. It's minerals in there. Okay, so inelastic scattering, it's important for modeling light field and comparing models with data. You've got to be careful about what you're doing. Raman scattering, interesting for lighter remote system. Oh, here it is. Tom Walter is the person from working on it in Germany now. CDOM fluorescence is important for measuring CDOM. Not as big deal in natural light field in what I think, but not necessarily everyone thinks, especially, well, I'll leave it there. Oil fluorescence, important for detecting fingerprinting oil, not so much in the natural light field. And mineral fluorescence, not in the light field, but important for identifying minerals.
Well, unless you had sediments that were made from fluorescent minerals that were suspended in the water.
Yeah, but the amount of that, it just really, yeah, I don't know. But anyway, yeah. So any questions? You can stop me at any time too. You didn't have to. No questions. Okay. All right. Well, I hope you enjoyed that. And I'm done. So you only have to listen to me for 3 other lectures. Yeah.
You said that there for a longer lifetime of the intermediate, there's more chance to forget information about the photon. Can you translate that into
Sure. So I told you about these Raman scattering, the volume scattering function effective of the Raman scattering is pretty close to Rayleigh scattering, okay? Because you have this virtual state that's has to have a very short lifetime, because otherwise it can't exist. So light comes in, comes out, it remembers which direction the photon came in from, and so you get the scattering. Looks like Rayleigh scattering. If you have a particle of phytoplankton there, it absorbs the incoming light. It has a lifetime that's long enough that it sort of forgot where that photon came from. And so when it emits, it's going to emit isotropically. Okay, it's also, yeah, it's also the polarization during the time that it's absorbed that photon, whatever the polarization state of the photon is, it's not going to maintain that polarization going out.
So it depolarizes.
It depolarizes.
So it absorbs polarized light in fluorescence. When it remits, it depolarized.
Yeah, so fluorescence is a depolarization, has a depolarization part. Well, it doesn't send it out in any pattern. I mean, it doesn't remember. It loses track of where it came in from. Sort of forgets.
The energy is heavily excited in the electron state, a higher electron state, for a long enough period of time that when it remits, it just remits in all directions, as opposed to re-emitting proportionally to the size of the particle, which shorter term elastic scattering knows exactly what the light's coming in, scatters more in forward direction, backward direction, equally forward, back, middle. So, but the excited state staying there long enough, and that energy gets lost if you emit.
The way I think of it is in Raman scattering, here you've got this water molecule, and the light's coming along, and you go the water molecule, and you go the quantum mechanics thing, and the light gets off. That happens on a time scale that it takes light to go past an atom or a molecule. So that's like 10 to the minus 15 seconds. Whereas with fluorescence, here's this chlorophyll thing, photon comes along, it gets absorbed, and it bumps the molecule up to the excited state, and it sits there forever, like 10 to the minus 11 seconds, 10 to the minus 9 seconds, which is, like a million years to me. And then the energy level drops back down and it emits a new photon. And that's, I kind of think of that as a brand new photon. It doesn't know anything about how the atom got excited by an incident photon. It could have gotten excited by just bumping into its neighbor. So in that case, that new photon just goes off in any direction. There's no correlation either in energy or in direction know, I'm running down the road and I bump into a tree and it's all over like a hundred per second. And I remember where that tree was, what direction I was going, what direction I bounced off.
I understand that it doesn't say longer for right?
I think it's because pollution is different.
It has to do with, I'm like going back,
Yeah.
trust me, but it stays with the electronic configuration, right? So it changes what is the longer. Go back down. I might be crossing that, phosphorus.
Even longer.
Yeah, if you look on the web book or the oceanography book, there's a big section on all of this thing that triplets stuff and whatever that's under the theory of fluorescence section. If you look for that, it's got a bunch of stuff.
Doesn't like where chlorophyll doesn't, people have tried to explain the chlorophyll forever to me, but doesn't it like it absorbs the energy here and then transfers the energy somewhere else? And it's at other places where actually the fluorescence happens. So there's an energy process.
There's some physical separation of the charge that happens across the molecule.
Mhm.
And then when they're in the molecules themselves, more so.
Mhm. So there's lots of stuff going on.
So fluorescence happens from 400 to
Yes.
Yeah, because it doesn't depend on this discrete energy level, it makes things virtual.
so you can quantify the change in wavelengths of energy based on like the energy wave energy. I feel like the first one to quantify for fluorescence, like the change in energy wave. Can you do that just in no, for fluorescence.
What was the question?
Like, how do you know, like, so how do you know the change in wavelength?
So it's constant for most molecules. So for chlorophyll, it always absorbs in those electronic energy levels, right? So there's the main qubit, 40, and then there's a couple of harmonics, vibrational harmonics in the UV. In the red peak, there's a couple of vibrational harmonics also in the green. So it can absorb at those discrete bands associated with electronic states, but it always fluoresces at the same location. That's not true for other molecules or mixtures of molecules. So I'll show you that in the next lecture. But there's this idea of, creating a virtual state which appears to allow you to excite at any wavelength and receive from at some known shift. Through the entire spectrum. You get blue, you get blue, you get green, you get green, you get. So it doesn't matter as long as you're excited. There will be some of this inelastic scattering walking because of water response, right? You can see that also in CDOM fluorescence. You get excited in UV, and you get some spectrum. You just keep getting shifts in the emission spectrum. But it's not due to any one molecule doing this. Because you have a suite of molecules, each of which has their own absorption properties and their own emission properties. But because it's such a mixed match, you see the continuum in the emission as we change our energy between. So I'll show you that.
It's maybe beyond, but like Raman spectroscopy is just using this to identify.
Yeah, so water, Raman scattering in water is fairly weak. It's pretty strong in a lot of chemicals. And so we use it, Raman spectroscopy is using excitation somewhere, looking where the emission is, looking at the energy shifts.
You use those signals, those like plots that are showing up wavelength and wavelength to like fingerprint stuff.
Yeah.
What other molecules have
It's a common technique in chemistry.
The calculated marker R is H1W1, the smaller wavelength, or the bigger?
If you look at this two curves, the way I figured it out, like the paper wrote it, the reference I looked at, you tell me. But what I figured out was the widths of both those peaks looked about the same on the graph. And one was bigger than the other, and the R factor was bigger than one. So I figured it's the bigger one over the smaller. Awesome. Okay, cool. Yeah, I actually thought about working with Patty to look at using Raman to look at microplastics and seeing whether we can figure out if we ground up mollusks. Can you get a strong enough signal
If we figure out how many plastics were in the muscle.
in the muscle? I don't know. If there was a spectrum I was going to borrow or get this company to lend you, and I don't know. I was thinking it could be strong enough to split inside all the way. Anyway, so I'm done.
So what time is it?
It's 20 after 22.
So you guys want to do 10:30? So I know you have the part.